digital safety. Programmability, so Axel gave an excellent talk yesterday, and he talked about the challenges being transforming user cases and software-based requirements back to the hardware. And 5G is inherently going to be very programmable. It's not just going to transfer audio and data or SMSs, it's going to transfer a mix of virtual gaming, video, audio, Teams, Zoom calls, right? So you've got to be able to program these systems dynamically through software, but also the impact is on the hardware ecosystem as well. So security is an obvious one again, because of OFDM being used. Security would be also an interesting one, but regardless of OFDM used or not. But the other critical thing about 5G hardware, which strikes me as very important, is this really small-sized antennas, which are basically going to be running potentially on batteries in the long term if you're going to roll out 5G across the world, in parts of the world where there's no electricity even. So you're going to be building low-power chips, highly area efficient, with all of these MIMOs that are in large quantity on a 5G antenna. So there's a lot of, as you can see, 7 or 8 different requirements that are actually exercising pressure on a 5G chipset, whether it is the infrastructure, it is antennas, software programmability. So things are looking interesting, and I think Axel can share more insights on what he's going through, but that's what I think is going to be needed if it's not already the pain.
I think Ashish brought up some very important points, but some of the points he brought up are probably not the most important yet as of today. And just talking about really safety, security, power reduction. Let's face it. Just looking at some of my colleagues in the audience, this is probably some of our software colleagues will completely ignore it. Like power reduction. This is probably some of the challenges where we as an industry also really have to transform. Because as of today, this is really the last topic where our product development would even think about it. Mm-hmm. And this is for sure, when just looking at the world around us, we have to change it. I fully agree, but we are not yet there. As of today, our challenges are just on complexity, late requirements, the topics I mentioned earlier. Safety, this is something where I know it's getting important, but for me this is an interesting question, because what does functional safety means when you don't have a safe network in between? So what are the requirements on the hardware? How tight can they be? When the channel in between, there is no functional safety transmission channel. We have to learn how to deal with it. It's a very interesting discussion. Security, this is definitely something where when you're looking at 3GPP, there are a lot of new requirements will come. I think some of my colleagues were saying, okay, this is a job guarantee for us, because maybe in some years we need to replace all the chips, because all these chips now need to have security features. So then we have all these additional features, and then this will be some of our challenges in the future.
It's good, right? To keep everybody in jobs, right? And keep everything secure.
Yes.
So I think to add to this thread, what Ashish and Axel are saying, at real intent, when we talk to our 5G customers, what they're telling us, it's even one level before that. It's just saying complexity is exploding. Yeah. These are designs that are not repetitive. These are designs that have new, very complex algorithmic blocks. And now they're looking at significantly more power domains, significantly more reset, significantly more retention areas, significantly more test, stability, observability. All of these systems have to be tested, right? It kind of indirectly connects to safety and security you're talking about, but just the testability. And the current methods are just not keeping up, primarily simulation. So our 5G customers telling us, what can we do to take the burden of simulation? What can we do earlier? What can we do in more methods? And basically being able to meet our time to market. So that's some of the challenges we're seeing. And again, we're probably going to speak to solutions more, but right now at the problem statement.
Okay. So I'd like to add a little bit on that. 5G, of course, it's really a beast. And if you want to structure the discussion a little bit, maybe it's a good idea to break it down into a bit more manageable pieces. On the one hand side, we see the public 5G networks. Public 5G networks, their reference architectures, it depends whether you're talking about the core part or the radio access part. There are very different challenges in this. But the next dimension is if we're talking about the private 5G networks. So private 5G networks, they're typically tweaked and tuned for one or two dimensions of the many dimensions you have in 5G very specifically. So really to go to the edge, for example, latency. In industrial context, if you're talking real time means not seconds or milliseconds, it means microseconds. So here there is a much tighter interaction in the radio part, for example. So to foresee all the differences, all the situations which might happen in the channel to compensate that. And I'm also very convinced that most of the challenges, they are not brand new to the whole verification and design expert domain, but maybe it's new for this specific part, because the integration of the A to D conversion with the digital signal processing in the front end, that was also a challenge for the optical networks in the past, and it's still a challenge. And this very same challenge now comes to radio, at a very different scale, of course. But the technologies, I think, in very rare cases, we are calling for disruptive new technologies. It's more to use technologies for design and verification at the more efficient and effective level. And the complexity of everything means that we need to coordinate the activities much better and much more structured than we potentially did in the past. I don't know, Axel, you are closest to the field.
I think, on the one side for sure, private 5G networks, it's a slightly different challenge, but when we are just talking about chip design challenges, it really, honestly, it doesn't matter for me right now. But I think you brought up a good point here, is that in principle, the main challenge is just the complexity, as I also noted it a little bit yesterday. It's the complexity of the single chip, and it's the complexity of the product, which for sure might vary, but at least from an infrastructure point of view. Other topic we are having on the baseband side, where we are having some of these challenges. You also mentioned all these different power domains and clock domains, because to be honest with you, I think the number of power domains on a networking chip is not pretty big compared to a baseband chip. And I have been in the baseband side as well beforehand, so I know what we are talking about. So but in the end, it's just chip complexity, product complexity, software complexity, requirements late, and this is something. And software, talking about the interesting discussion we had beforehand on all these shift left activities, which we are all getting a lot of push into this. But the biggest challenge still remains when I want to do shift left activity. It also means that I have to shift left a resources profile, which is normally not really anticipated by our finance guys, because their expectation is that the, for example, software profile remains flat, and then we have a minor up to major conflict. And this is, I can still remember my times. It was 10 years ago, and Intel already at this time, we developed a virtual platform, and it was took a lot of extra effort, and it was then waiting for 1.5 years to get the product software team up and ready for this software. This is then sometimes reality bites in software shift left. And I think there are a lot of good activities, but we have to tackle not only the technical concepts, but also the resourcing, the financial, the budget topics.
And I think for this shift left, to come back to software, a very valuable contribution is open source, of course. And there are strong software stacks available in the meantime. But what we also hear in the domain is that even though there is open source software available, many of the companies, they are going for the proprietary stacks, which go beyond the capabilities of the open source stacks in the one or the other dimension. So in theory, we could support this shift left significantly through the open source reference implementations to a large degree, but the remaining 5%, they come from the proprietary stacks on top of that.
Just wanted to add that 5G is just a misnomer. Today 5G, tomorrow 6G. The challenges are for tomorrow. We cannot use today's methodology. So we need innovation, not just from the companies, but whole ecosystem and EDA vendors also should support this. So this is what I just wanted to chip in.
So I just wanted to say thanks to you, Uren. You brought up the challenges that some of your customers are bringing up and saying save simulation cycles. And Herbert made a very valid point that 5G is a beast, but at the end of the day, we have to break down things. And one thing I picked up on Axel presentation yesterday was that these use cases that they're not available all the time, and even when they are available, they are at a very high level. And to try and map them at a level of hardware so that you could actually build up a scalable verification flow interface to interface. In many cases, I think Axel was referring to these interfaces as non-standard. I think those bring interesting challenges, but I agree with you, Axel, that some of the points that I made on safety and security may not be your headache in 2022. But believe me, if 5G was going into the automotive industry, we won't be able to get there without those aspects, and your life is going to get more interesting. So I take your pain points on board about resourcing challenges and shift left. But I think my main concern, and I was mentioning this to Axel and Herbert before the panel, I think the problem largely with industry that we operate in is we always look at slices of problems that we like and fall in love with. And whether it suits us as an EDA company, or because, like in Axel's shoes, he is responsible for a bunch of things, so he's looking at specific problem targets and looking at solving them in a specific time. But I think we need to take a look at all of these problems in a holistic manner. We can't just look at functional verification and forget about deadlocks, for example, or safety, but not look about performance, power issues, but not look about security. I've looked at designs where I've picked up bugs in processor domain, not necessarily 5G. They are low power, they're low power optimizations, but they're actually breaking architectural requirements, they're breaking security protocols, the confidentiality, integrity, availability. You could never use their processor in a functional safety environment, they would break the lockstep. So it's not like there's one thing that you need to look at, solve it, even if it is a directed test case or a UVM random test. You know, who actually makes a call that the whole lot was verified in this proportion? I think that is the hardest part with a domain which is increasingly dependent on software and use cases. I think that's what makes the 5G life more challenging. By the way, one thing I picked up on your talk, and I wanted to say to you that actually the GPU domain is also very highly sensitive to hardware-software interaction. And I think I see a lot of parallels in the size of the GPUs that they are and the way the software drives. So I think there are things that we can learn from, and I think Gabriel is going to slowly herd us into that direction.
Actually, what you're saying is quite interesting. You mentioned GPU, CPUs, and so forth. And so what 5G is out, so designs have been done, and we are preparing for the 6G. So what will be probably interesting to know is what are the differences with the designs that we know the best, like CPU, GPUs, AI, ML, accelerators. What are the differences with the challenges we are facing with these designs and the ones that we faced and we are facing with the 6G coming up? There are some commonality, things that we can reuse, adapt, enhance, or we trash and we start from a white paper.
Okay, maybe I think, so as of today, it's probably, one simple thing is it's just a little bit more about even more complexity. Okay, that's an obvious thing to say. And yes, security, safety features will come in. I'm even a little bit more concerned about more technical topics, which are also related to verification. They're also related to power saving. Because, just remember when I talked yesterday about, our lifetime experience. And honestly, we are pushed to 5 nanometer, 3 nanometer. I have no clue what is the lifetime expectation of 3 nanometer for specific power profiles, and this will be quite important. And because our customer for sure would love to replace the chips after 5 years, and they would for sure be very happy about this. But this is something which is challenging. So from our side, I think we will even, this is another challenge, we will more go into this kind of automotive requirements, like, where you have all these requirements on the reliability, because otherwise we are really, and all of us having there some big troubles. This is for me one of the bigger challenges. Then the only really big difference I see as of today on 6G is more AIML, but what it really means, I must say, I don't know yet.
I think we're all trying to figure out what
it means. We are still figuring out what is the impact there, what it means in the end, still to be seen. I think we are all working on it,
correct,
but what the outcome will be might be a little bit too early.
Yeah, so I think to tie maybe the previous discussion also, Anil's comment about the tools and the technologies have to evolve, and connecting to what is the difference to designs such as CPU, GPU, AI, machine learning. So, we're dealing with both type of these designs, and I think the biggest change is that, or let's start with commonality. I think it's common to say that those designs also experience a significant increase in capacity. Multi-core GPU, multi-core CPU, all those AI ML chips, they just have a lot of repetitive blocks. Where we look at the 5G, our 5G customers, that's not the case. It's just a lot of complex, big designs that are new. Or, they also need to support all the 4G and all the previous standards and so on. And a lot of this now has to be verified. Most of the time goes on verification. So all of this has to go verified together. And that's where basically I think a lot of the methodologies, and again connecting to Anil's point, actually break. And the time they have to bring those products to market is not sufficient. So they're starting to cut corners in simulation. And when I say simulation, it's simulation, FPGA, and emulation. So we're jumping a little bit to maybe potentially solution space. Where do we see this going? I think Herbert talked about shift left, and I fully agree. I think shift left is in 3 different dimensions. It's the virtual platform at the system level, it's the software side of things, but it's also the chip design technology, the chip design methodology. What can I find, what kind of scenarios, failures, bugs can I find early using different techniques, right? Formal, static, and simulation. So I'm not pushing all the verification effort to the last portion of the project, where obviously I won't be able to do it. So I think that part. We also talk about shift left from our standpoint, using static using static techniques, but basically using any technique available and evolving of design technique and verification technologies in order to do the shift left also in that dimension.
So if I may add on that, I really like what you just said, and I think it's important to care about the aspects along the design phases. So when we start from the architecture perspective, and I think to make it easy, we should for the moment forget about the core network, but more focus on the radio access, because this is more heterogeneous, more application specific. The architecture verification it's the very first challenge. So it all means that we need to have good predictables on what's possible in the chip implementation later then. And I think with the upcoming challenges for 6G, it even drives companies more to systematic model-based systems engineering approaches, leveraging either code generation from high-level models or high-level synthesis or the like. So you need to carefully distinguish between what can you verify at the abstract level in the context of architecture verification upfront before you go into the next level of abstraction, which is then typically RTL. And in RTL there is the full bunch of verification technologies, from simulation, formal, hardware-assisted verification and whatsoever, and to make this available for the next level of system integration again, because even though we are perfectly able to verify subsystems, if the specification around is stable, if the standards around are stable, And even though there are design IPs and verification IPs available, we all know that there are so many parameters to configure the behavior of those IPs. And for sure, the one configuration you're using, it's not yet silicon proven somewhere else. So for this reason, this system embedding is a very key thing.
I would fully agree to your statements, but I think you missed one important aspect out. I think you talked about static sign-off, formal verification, MBSE. I think these are all important components. But when you are asking me, one important topic which is missing is really very early performance innovation. Because I think, because when we're talking about these so many programmable devices, and I think you brought up the points that we have to combine more and more PDs, but their MBSE is also not helping us, to be honest with you. And this is something which is often missed out, or is coming too late, that you're really making sure that your system together with the Ps, with all the buses and buses to the external and buses externally, have enough performance.
Exactly.
And this is one of the worst mistakes you can do very early, because when you suddenly realize, oops, I need a little bit more CPUs or bandwidth or memory, and this for me, I think it's getting even more important with 6G.
So let me give you a practical example on that. Many of you might know that we are very active in 5G for industry. Practical example is the industrial shop floor, a manufacturing shop floor with AGVs, AMRs moving around autonomously. And 5G is one of the enabling technologies for communication there. So the first challenge is that we need to ensure that there is a radio coverage in the whole shop floor perfectly suitable for continuous communication. We must not lose communication links. Then there is disturbances. This means the wireless communication channel, it changes dramatically across the shop floor. So we have a digital twin which is able to model where are the potential different locations of communication partners and what is the coexistence of communication. So if you have hundreds of AGVs, they might either communicate in a nice schedule, or they might communicate event-driven and all at the same time, at the same location, which confuses your mind more and whatsoever. So this type of abstract information on the use case to be connected to the implementation, which Axel just brought up, in a digital twin of the radio, including the backbone, so that you can understand if these messages are correctly decoded, encoded, transferred, handled, and what's the latency for that situation. So this is the 5G digital twin we are heading for, which we partly have implemented.
They had very valid points on system integration and other interoperability things. So Samsung and other leading foundries are working on moving away from monolithic ICs to 3D ICs, where we can have different nanometer technologies for RF, for GPU, CPU. So it's going to be hybrid heterogeneous. So I think a design technology co-optimization kind of a methodology is needed for effective and bug-free designs, so that we can have verification at scale, like economies of scale. So we can support the same 5G chip can be used across multiple frequencies, like from 600 megahertz to 26 gigahertz, and as you rightly pointed out, the quality of service, right? It is becoming paramount for any kind of devices, and 5G is not just in handsets, it's going to move from handsets to robotics, where latency is very, very significant, important. So yeah, I think everything is valid. Again, not just 5G, for all future designs, I think these kind of innovation or methodologies should start, EDA vendors or whole ecosystem should start flourishing in this aspect.
So I just wanted to quickly say, I think the problem we are talking about 5G in particular is very interesting, because if you look at processors and GPUs, you already know what kind of software is going to be running on them. That comes from the instruction set architecture or use models that have matured over the years. 5G is so new, as Axel also pointed out, the use models are not clear. How would this chip be actually orchestrated in this field? I think Herbert was also alluding on this. And I think unless we narrow down this main challenge, which is what kinds of different software is going to be running on 5G, what interfaces are standard interfaces that the chip vendors have to implement, and then they have to be programmed in this and that way. That would ease the pain on the hardware stack in terms of the design and verification. But if you take whatever I said out of the context now, and then you just look at a 5G chip as a purely hardware design, then I would say anything and everything that happens on a 5G chip happens on any other chip. At the end of the day, we write very well VHDL, we have got pins in there, buses, processors, etc. So we could learn and leverage everything out of the ordinary, I would say, meaning everything else.
I have the question. I have the question based on discussion that you had at the. So it looks like that for the 6G we need something different. So we need we have learned from 5G that what are the key challenges. So we face the key challenges, and these are educating us for the next generation 6G. We mentioned the digital twin, for example. Do you see for the 6G new methods that will be applied, that will take place for the design and design verification of the next generation of this communication solution?
So I can speak from a design technology perspective.
That's all right.
I mean, from design technology perspective, I think we're seeing more of the same. Basically, it's all those things that we just talked about 5G will just be bigger. That's what our customers are telling us. It's just bigger, more complex, and with the same challenges will be there. But it's already reaching a point where the current verification techniques are not keeping up. So we believe that the verification technology and design technology will have to completely evolve or reinvent itself to meet those challenges because it's starting to break down. So basically new techniques, new methodologies. We talk a lot about shift left here. I think this was, Herbert's example was a perfect example of shift left in the system level and using digital twin to emulate things we were not able to do a few years back. You have to have the chip to test those things. The same thing will have to happen also, again, we're from design technology and verification technology in the chip design flow. Otherwise, we won't be able to do it. So advanced technologies need to be developed, advanced mathematical models to reduce the burden on designer using mathematical search and analysis, proximity, isomorphism. These are some technologies people in EDA at least exploring in order for designer to see less but do more. Basically, the tools, the technologies have to focus designer to what they need to see.
Yes, sir. I think Oren rightly pointed out. I think we will be hitting a glass ceiling if we use standard or a very traditional verification methodology. I think digital twin or some kind of a standard should evolve from Accelera, or UVM should take that new challenge to add this digital twin to make a hybrid heterogeneous system verification.
Okay, that's from my perspective in the end, because I think we're talking about it's still about a complexity problem. So in the end, I think so where most of my colleagues here also talked about is somehow some ways to break down the complexity. Right? This is you brought up an interest on this chiplet or 3D integration, because in the end, what is it? By the way, I don't see the specific challenges. I just see the benefit, because again, it breaks down complexity. So suddenly, instead of having a chip which is so big, you're having 3 chips which you can simulate separately, then you can create a model out of it and can simulate it together with the other. It makes it, yes, at least, you don't 3 times less, but it's even more because we know complexity is not scaling linearly. Yeah, and the same is probably also on verification. Even on the software side, I think we all need a little bit more standard interfaces that we have. Yes, it will decrease efficiency, but it will increase the possibilities that we can achieve it. I think we had before, and we had this interesting discussion on software. On my side, it's always this kind discussing with the software guys. No, we cannot afford additional software layers because it decreases the efficiency. Yes, it might be, but it might be also handleable for us, because ideally we would have a case where we can run the old software on new hardware and mix and match. But this is honestly not always possible. I think we are now starting with this, but there's still too much resistance. And I think this is again it's like, could you imagine today still doing a microcontroller SoC without a standard bus? And by the way, without a standard bus, just from a chip perspective, the chip certainly would be more efficient because you can create your full own bus. But let's not think about it, would it be still feasible? Could somebody validate it really? I think this is something what we have to learn on all levels.
I think one thing that stands out with 6G, in my sense, is it's going to be very heavily compute intensive, because I think we will see a convergence of HPC and AI. And with edge devices and the concept that you can actually compute things on the edge, and if you think of doing it in a power efficient, performance efficient way, I think it is only a matter of time the architects would try and then put interconnects in there. There would be some fancy concept of high processor computing, high performance computing on the nodes, on the devices. So I think it's coming, and I think it only is a matter of time. One major or two major vendors would take a leap ahead and would try and demonstrate the prototypes, and then suddenly it will be the next big thing. I think if you start to think of how much machine learning will have to be done, not just locally but also exchange data on a network. So I think it would be 1,000 times faster, they say, than 5G.
So I think we are back in the old discussion to understand how much can we do on a general purpose ISA.
That's right.
And how much do we need to do on application-specific hardware architectures. Yeah. And for the application-specific hardware architectures, of course you can run all your AI on GPUs. But there are architectures which are significantly more efficient than GPUs for specific AI workloads. Yeah. And that's the fundamental question, I think. And on top of this, we have the design technology optimization, so how to better leverage the capability of the transistor for what we're going to do, so that we have well-balanced timing passes and not having 2 or 3 logic layers in between a clock cycle instead of having 20 capabilities. So this mix, I think, is the challenge. And this heterogeneous compute architecture exploration, so the design space exploration, architecture exploration, this for sure will be a new dimension of challenge in 6G compared to 5G.
Yeah, exactly.
I think there should be again some standards for these workloads to be prototyped or modeled or simulated before we code the RTL for this. So I think we will be moving from standard register transfer level to, I think, next level, which is high level synthesis, and from prototyping or models we'll come up with the IPs which are self-architected. We just give some of the parameters, and probably I think that is the direction the designers or the architects should look into.
I'd like to throw something back at my colleagues on the chip side and the system side, because I think that a lot of pressure they're putting justifiably on EDA vendors. You guys have to, and design vendors or foundries, you guys have to scale, you guys have to reduce the complexity or help us with the complexity. But I think that also from a design architecture point of view, there is something to do about designing things in a more structured way, so the complexity is really broken down, so the tools and design technology can handle it. For example, we work with a lot of compute vendors, right? So building large servers or clients, and it's all, a lot of cores. Designs are very big. They're probably as big as the networking chip and the 5G chips. But our design technology and verification technology scale very well. We have not experienced the same type of issues we're seeing with 5G and other networking type of
the software model that Alex.
Not only that, it's very regular. So they've broken down the problem to the complexity, exactly like Axel was saying and Anil was saying, in a way that allows the design technology and verification technology tools to scale. So I'm kind of throwing a little bit back to the design community and system community as well.
That's an interesting call because right now this is for sure partly really coming from the architecture, because we have different components. I think somebody mentioned this already beforehand. It's unfortunately not the case. Let's also realize when we, for example, there are also initiatives, at Nokia, for example, we are thinking about using their more smaller processing nodes. Yes, this might be helpful on the hardware side, but honestly, it's a big mess on the software side. So you're changing complexity here, it's changing complexity there. So I'm not quite sure whether it's helping. And I would still not let the EDA companies out of this demand that, hey, get more standard interfaces, please, on your side. Because this is right now for me, and I made this statement yesterday clear that it's, in principle, different software tools are not really working together, so this is nothing I can do. This is something where EDA companies should think about it. This is, I must admit, I would not fully take it. Yes, there's some truth in it. It's for sure sometimes we should make a balance between where do we want to have the complexity in the end. Do we want to have the complexity on the hardware side and more on the software side? And there are some people who say, I would be better to have it on the hardware side because then at least it's better controllable. I can maybe not fix it afterwards, but for sure there are different opinions on this.
I think so you made an interesting point on EDA interoperability being a challenge, and certainly tools are getting better. So I'm a formal verification guy, so I use formal 24/7. That's what we do. We do processors, GPUs, interconnects. We haven't done a 5G yet. We've done Ethernet switches. Tools I use have no problems with complexity handling. We do see occasional crashes, but as a reference point, I've compiled a 1.1 billion gate design, about 400 million flip-flops in a formal tool, and I've been able to do functional verification. Now, the challenges in my view are not so much, of course, what Axel said, if I want to now use a different tool, how do I port the results, etc., especially coverage. The problem I have is knowing what I'm going to verify, the requirement space. Now, in the context of non-5G work, this is slightly more manageable because of the maturity of use models. We still rely on specs, microarchitecture as well as architecture. But if you're not going to tell me what this chip is going to be used for, or the limits of the interfaces, whatever that interface may be, ad hoc, non-standard, standard, then I don't know what I'm going to verify. I don't know what I can cover. So for me, the tool complexity and the issues with tools maybe not so good is, in my mind, not even a very significant barrier in making me productive.
But maybe
this is where I'm coming from.
Maybe you can reverse the exercise, say, I'm able to tell you what this thing is not able to do.
That's exactly what we do in formal. So in formal, we are able to prove. So we go to the designers and say, okay, you said this was going to be like this. Is that what you meant? Of course, yes. And then the second question comes, are you sure? And that makes them think. And then what happens is a discussion where we refine the scope. And the one thing I just want to bat for formal here, which is an amazing thing, is that it can deal with unknowns in a much better holistic way than simulation techniques can. Because when you don't know enough, the tools are bombarding all kinds of stimulus for free. So sometimes it reaches points of failures that are spurious and it burns your time in debugging them. But that also has a side effect in exposing bugs that nobody thought of. I have half a dozen examples in my mind where architects said, we didn't even think about this scenario. And I hadn't even gone down the path of fully constructing the interfaces. It was only just day 3 of the work, right? So there are benefits in combining all of these technologies in a sensible way. I know formal is always considered to be a bit of an outsider. I think it's getting better, but I think this fixation on simulation-based verification and heavy reliance on simulation, even for those verification tasks that could be done within days with formal, that needs to change. I'm totally unembarrassed to say this.
But I think,
see what I say to say.
I think it's a yes and no, or yes but.
Yes and maybe would be a good.
Yeah. I think yes, it's obviously that sometimes we are still not using formal verification enough in a lot of areas where we could even have done it, and there's for sure sometimes resistance. my butt is coming from the face, and I would love to have more discussion on this, is how do you use formal verification in our data paths? How do you make sure that, you know, the MATLAB data I have provided is going through this system? I have not yet seen a solution. I would be happy to
not
see
in
some.
5G maybe, but in AI/ML there are plenty of case studies.
Yeah, but
people
this is the
verifying designs similar to so FIR filters, FFT, anything Axel that you build in Verilog or VHDL, or if you can simulate in UVM, is verifiable by formal today. I can tell you spot on. I can at least think of 3 main vendors who all have solutions in this space. If you can code it in VHDL, we can verify this informally.
I had this exercise 1.5 years ago with one of the big, very advanced formal verification companies, and honestly, we ended up with something which was like a bus controller case, because this was the only thing they could really do.
Yeah,
so
things are
yes,
changing.
in theory, I say yes, but I really would love to see them work.
It is one of those things I just wanted to say, like processor verification is largely dominated by UVM, right?
Yeah.
We have examples of 64-bit multi-threaded codes being formally verified. Now, depending on who you talk to, people would say, oh no, you can't do it. But we have done it, we have results, we can show you the methodology. I think with regards to the algorithmic verification that you and I were talking about, especially in the context of 5G, very heavy with compute, honestly, I'm not the one making these tools, so I'm not batting for any one of them, but you're welcome to talk to each one of them, and there are actual production grade solutions that are being used by other companies for verifying those kinds of designs, so it might be worth looking at, that's all I say.
So yeah, I had to look, so I'm not yet, for sure I'm always open for new solutions, because for sure going there into formal verification would definitely help a lot. Especially, looking out into where, also fault, for potential faults. But I still have to see it.
I would just like to add one point. Formal verification and functional verification share a frenemy kind of a relationship, friend and enemy. But I think soon, because static formal, on the static side, it has really taken big leaps on the static, but on the dynamic, there are challenges on convergence and state space exploration problems. I think
there are challenges.
Experts like us.
Yeah, there are no doubt there are challenges, right? We see those complexities also hitting, but everything is about how you begin solving the problem. Everything is about problem solving. With simulation, it's not going to be any easier. You're going to spend 4x more in bring up of these test benches, right? We would be able to tell you in week 4 of the startup, this is not going well in this direction, you might need to do this. We'll come back to you in the first day to tell you what we would need to contain the complexity. There are no surprises, but unfortunately or fortunately, there is no shortcut, right?
No.
With UVM, if you look at the number of people in the world and the companies involved in refining the methodology and creating a convergence point, we still have challenges, right? So formal is much smaller than the scope of users. So I agree.
So we are okay, we go back. We are okay, we go back to the 6G. It's becoming a debate
Someone wants to
about.
ask a question.
Yeah. Which? Oh, okay. Yes.
We can't hear you very well.
Couple of questions there, right? The first one was when you said the spec for the 5G chips is very vague, or it's not clear, which poses a challenge, but why does that have to be, like, considering the push for domain-specific architectures, why does a chip have to be generic and not have some purpose, and then you have a spec, and that's how you define your spec, and once you have a spec, you know what your bugs are going to be.
I think what Axel was referring to yesterday, and I mentioned it a few times, and we discussed this, is I think the use models for 5G are quite a few many, and they're not, the maturity of these models is not fully understood, or if it's understood, it's still trickling away. when did we start building 5G chips? Axel, you could tell us, right? A few years ago, right?
Yeah.
So if you look at processors, GPUs, etc., even networking devices, been using them forever. So the use models have matured. I think the challenge that that Axel was mentioning was he's building it under some assumptions that it would be used in a certain way, but then people use it in ways, in models that were not fully grasped in the beginning, and that's where the challenges are. And if you imagine how big these chips are anyways, and now have to shoehorn all of this back to the hardware side, is quite painful.
It's, just as an example, talking about the huge number of carrier configuration you have in a typical DFE device, and which is when you're just looking at the pure statistics, there's no way you can simulate all these dynamic changes of carrier configurations in the end. When none of your customers is telling you any kind of specific use case, you can put a finger into the wind and do an estimate. And guess what? Customers will later come up with some kind of different configurations you never considered, and hopefully they are working. But you can be sure that some of them you never validated before. This is, just on a high level. It's in principle because with all this programmability and configuration possibilities, it's simply not possible to validate each and everything. Even when it's specified, there's something specified, but it doesn't give you good direction for verification, except we would spend 100 years for verification.
Oh yeah, so actually, not only would they bring you additional requirements, they will tell you to ship it 6 weeks sooner, right?
On top of that.
So that's the problem.
Okay.
And I think to just a quick follow-up to this, I think you're seeing from a system level that also translate to a design technology and verification technology, because now the designers building this chip for so many use cases, and every small block is fully configurable, so the current methodologies for verification are just breaking down. Where you look at something like we talk about compute, like Ashish was saying, it's clear what software will run on it. There are few configurations. Those chips tend to be highly configurable, and just no current verification methodologies cannot cover everything in reasonable time.
As Alex rightly mentioned, we cannot have a line-to-line verification of these standards. These are open standards. Implementation is, industry-specific or, company-specific. Right? Standards are there. You can adopt few features of it and verify accordingly. Right? So that is one more point I want to add.
Thanks for that. My second question was more pertaining to formal. So, why do we always put out a question, formal or simulation? Wouldn't it make more sense to have formal along with simulation? Because
so that's what we do. So all our customers that we work with, they all use UVM. They often have formal teams themselves, and when we formally verify a block, we ship our assertions back to them, and they get integrated in their DV environments in the following week. And if there is any discrepancy that we find, because we were working with a spec that was outdated, or because there was an email communication that was slightly out of date, we fix it. What I was trying to say is, for certain problems, and there is a large set of problems, which you will greatly benefit by adopting formal sooner, because it will find bugs quicker and corner cases, and you can build proofs as well. And you have to think of the verification problem. My observation is, when I work with customers and in general have panels like these, when you say the word verification, people think of UVM or emulation. And in many cases, people already know. If you say, what are we going to verify? What are the requirements? When do you want to tape out? They're already talking about how they are going to build their next UVM test bench into this. I'm not even going into how. I'm not saying use formal. But what is it, that problem you're trying to solve? I think that the discussions that are very interesting is, how do we combine these two technologies in a meaningful way to actually win? At the end of the day, we all want to sit in cars that are safer and fly in planes that don't fall off from the skies, right? And at that point, would you really care what was used to verify it, right? So I think I'm totally being agnostic here, right? But I'm only talking on behalf of the data. right? But understand, sorry.
Yeah, I think it's even, just to extend it more, and, Ashish made a valid point, but, it's in the end, when we are talking about verification, and I even mentioned it yesterday, it's verification as of today is way more than just functional verification UVM based. It's basically using all these methodologies. And our challenges is, as of today, to combine them and to get, a good, assessment of the coverage out of all these different tools.
That's right.
This might be for sure static sign-offs, this might be virtual, twin, it might be formal verification, it might be gate level simulation, whatever. But the challenge is that we have to combine it.
So the important thing is the completeness in the planning.
Correct.
If you have a complete planning, then the execution is quite simple compared to the planning.
Quite simple.
Quite simple.
There is another question.
50% job.
So an observation, and I'd like to get your opinion on this, is that I haven't seen any company succeed in adopting constrained random coverage-driven techniques without building an organization with that expertise. The problem I see with Formal is that go grab a tool and then try it out, put it on the shelf. They haven't built the same level of expertise in terms of in order to get the most out of Formal. Because you just can't buy a tool, push a button, and get the results. It takes a lot. So thoughts?
Yeah, so it's a very valid point, Harry, and this is basically hitting the nail on the head. So if you do not have a team of sustained expertise over a number of years, then things don't grow. I mean, there are 5 or 6 companies in the world who have managed to build big teams of Formal experts, and they are big believers in Formal, and they're doing big chips as well. Most of the others, actually, it's a bit dotted spotted. We see that too. We work with companies where they already have Formal teams and experts, and we work in conjunction with them, bounce off ideas, extend the methodology. But I think knowledge sharing is critical, but in a number of cases, it happens that even the teams that were doing Formal hadn't fully grasped the true potential of it, because they would start off in a direction based on where they learned it from. And that certainly can have very limiting, I mean, like Axel was also alluding, having spoken to another company, had a different perspective on what is possible and not. I think, I keep saying this, Formal is no harder or easier than UVM in terms of adoption. It is easier in terms of execution because we don't build UVM test benches with transactors. We do not have to write stimulus generation at all. But actually, what is that exact question you're going to ask in the project? Sure. What is it that I'm going to verify is the first thing. How we do this is the second part, right? So it is like, you have tools which are actually being able to accelerate the low-hanging fruit.
I fully agree with Ashish, and think to the point, Formal has a role, and the more you do informal, the better, because again, you're taking from the traditional verification, which is anyway now not converging. And on top of that, we're coming from a static solution point of view, so we're saying use more static, right? Because static you can cover some aspect. So you cover some aspects in Formal, it's not going to be the whole chip verification, not at all. But the ones that you covered in Formal, you don't need to do again in simulation or in emulation. The ones you cover in static, take for example CDC, right? People used to run days and weeks of, when I was a designer, we ran gate level simulation with timing just to check the clock. One flop that, went metastable and, it was a disaster. Today, most design houses, they run CDC tool, the static tool with some Formal, by the way, underneath. And they say, okay, we signed off, we don't need to do it anymore. So you take that aspect and you did it with Formal or static. And then everything that we have not figured out as a design community to do with those tools, sure, you need to go to simulation. So we're not, I think what we're saying here, and I think I'm aligned to what my colleagues here are saying, it's not this or this or this, it's this and that.
Put it in mathematical perspective, these are not mutually exclusive, but these are associative, functional.
Much better put.
Can I do a follow-up question real quick? The following question is related to domain knowledge, and I think you brought this up on your keynote yesterday. For example, I could hire a lot of plumbers that are good at building UVM test benches, but they don't necessarily have the domain knowledge. And I think that is really the big complexity we've got today in 5G and 6G.
That's right. That's the complexity that affects all of the design verification. Just trying to come to terms.
Well, there's a lot more domain knowledge in the CPU space.
Correct. So, once the optimizations kick in any domain, never mind the architectural layer, just understanding the impact of these optimizations and their connection with the architectural requirement or the software requirement. I think that the great thing about Formal is that once we write a check and it fails, when we're debugging it, in the next 1 hour, something useful happens, which is we get very intimate with the way the design is built, not looking to read the design, but understanding why something has failed. So the biggest challenge in my world of verification is understanding the domain knowledge. When we start a new project on any new design, weeks before we start it, we are prepping up ourselves to make sure we understand the design better than the designer does. Because if we fail on that, there is no hope in the world, I could say, I've verified. Because we are meant to be auditing his design or her design. So I think the challenges that Axel was saying, shrinking schedules and increase in feature set, changes that come in, those things are practical realities of life. We have to take it on the chin. But you made a very, very valid point, Harry, and I think this is one of the main reasons why things don't work out. I don't know what are the thoughts on the UVM side. I'd love to hear from you.
Just one question. There is another question.
Yeah.
2 questions.
Yeah.
We have 4 minutes left.
Okay, then maybe not questions. Just take questions.
Yeah, well, I have one question, because everybody is saying, this is so complicated, it's so complex, we have all this complexity, we have all these pieces, and the obvious question is, why is that? Is it actually necessary to make this complicated? It just happened by accruing stuff over time? Or could you say, yeah, we could actually achieve the same performance in a much easier way or simpler way? Is that even conceivable?
For 5G, I think this is particularly relevant because of the lack of use models that Axel was referring. And then again, if you want to make things faster and compliant with the known and unknown feature set, then that creates more challenges.
So just looking at the bandwidth and the algorithm you have to support it, I'm not seeing easily how this can be
implemented.
It changed to suddenly, magically, by some kind small, simple chips. So honestly, I cannot imagine it. Maybe I'm missing the fantasy or the smartness, but hard to imagine. It's for sure it's a fair question, but for me it's just when you're looking at the specifications which are under discussion, it's a very complex thing. Now, what you could think about it, what we discussed beforehand, that we are somehow creating a massive, complex software on top of it and running everything on a very simple hardware. But I would say this would not gain us too much. So this would be my at least short response.
And I think, connecting your question to the previous notes, I don't think the complexity will disappear. It's actually going to be bigger. But again, going to design community, have we put enough thought into how to break down the complexity, again, borrowing from the previous notes? Complexity will be big. Can we break it down into smaller pieces that we can verify them more efficiently?
There's another question.
Yeah, so I see that the discussion is going more on digital verification, formal verification, but on the other hand, the analog part, RF part, is also very challenging. So what are your thoughts about modeling, for example, if you want to model some transistor behavior, so where do you start, where do you stop of the modeling accuracy? So like Monte Carlo simulation is very important, and your model will only will be valid for one certain scenario. So, and the main challenges, main problems coming mainly from the analog. So the world is analog. So how do you want to deal with it?
And related,
I could take it. Yeah. Yeah, I fully agree. Analog is a challenge on its own. But I think there were really significant good steps forward in the past years. Monte Carlo is still in place, but it's partly replaced, or to a large extent already replaced by AI-enabled approaches. So you're no longer going to simulate the full range of Monte Carlos. Instead, you are kind of training a regressor on the full variable space or parameter space to understand in which corners you will find your outliers, so that you can get your 3 or 5 or whatsoever sigma range with 3, 4, 5 orders of smaller number of required simulations. So there are means in place, one just needs to use them, but the challenge of analog design, it will not disappear. You're just better able to address complexity in analog design with this in a much, much more efficient way. And then this is on the transistor level. Then at the next level, you need to think about the integration of the analog part with the digital part. There are also good means to integrate them, to ensure the interfaces on the functional level, on the timing level, for all the different corner cases and the like. So it's work which needs to be done, and there are means in place to tackle this.
And actually, to Herbert's point, we actually have been working and approached by multiple mixed signal design houses to bring static also to that domain. So basically, we're not in the analog space, but integration to the digital. There are significant aspects that could be done using static tools. So I think that's things that we are going to be seeing moving forward.
Yeah, and maybe just from my side, I have been in the RF analog domain a while back, but when I'm just looking at our systems today, I must say, the analog simulation is honestly not my greatest headache. It's maybe also due to the fact that we are not doing our analog chips ourselves, we are just using models. But this is, when just asking myself, you can say yes, but there are a lot of challenges. The challenges I'm having today from a system side, are more coming from the digital plus software side. It's for sure, but just from a percentage of challenges we are facing, this is my biggest headache.
Maybe one.
We can hear you.
Hello?
Yeah, that's better.
Regarding the analog, maybe you're right, but what about the RF? So at the end, crosstalk, for example, is a main problem, not on the chip side, but also on the application side. And the tooling is very challenging also to cover all the effects. So at the end, you are designing, you are tape outing, you are spending a lot of money for the mask. And in the lab, if you test it, it is not working.
But okay, there I agree that crosstalk indeed is an issue, and I just remember a recent case we had. But honestly, this most of the crosstalk cases we are having, which makes it even not easier, are more coming from the product level. Because I would say, as of today, the crosstalk on the chip level, it's for me not the biggest problem. The biggest problem we are having today, when we are because, for example, for base station, for infrastructure, you have to put this together, a lot of chips, plus RF, plus power amplifier, etc., together in a small package, and thus, guess what? There might be sometimes crosstalks, and we realize that, one of these PAs had an impact on the DDR interface, which was causing sometimes some issues at the customer. And this is, for me, as of today, this is less crosstalk on the transistor level. It's more on the system level. Very important one.
Also here, I think at PCB level and also at, let's call it box level, there are good technologies available to simulate this upfront. So PCB level verification, PCB level verification for immunity, that's solved. It's a hard work, but you can
exactly. Yeah.
That's
true.
For sure, you need one iteration, but not 10 iterations.
This is exactly what I want to mention. So you need several iterations because of the lack of the performance of the tool. So you have it's an interaction between the chip, the package, the PCB, and
the antenna.
application.
Yeah, the antenna.
So you have to consider the whole chain, and this is still some challenging topic for the EDAs.
Mm-hmm. But just in the context, it's less than a chip design challenge. It's really more a product or system design challenge, and I think it's still there. And it's partly just a discipline topic, right?
Other questions? Or maybe we can just conclude with a quick one. So what are the key challenges that we need to face for being on time in the market? If you just a couple of words to identify the key ones that you see on the space, at the chip, system level, software, whatever.
For me, the key challenge is really to break down the complexity. This is honestly, very simple. This is my biggest topic on my side.
Yeah, I agree with Axel. I think if we can find a way to map all these emerging software requirements as interfaces that could be mapped to the hardware, then to be honest, we can take it from there. We can do more and more formal. Yeah.
I can speak from chip design technology and verification technologies. So we define something, we say the three workhorses of verification: formal, static, and simulation. We believe all of them will have to evolve significantly, and design teams, verification teams will have to use all of them and balance what can be checked efficiently here, what can be checked efficiently here, and what eventually go to simulation.
Yeah, so to finally conclude, I think it's all about going from the application, so from the system down to the chip in a more or less seamless way. And there are a number of hurdles in between, and these hurdles we will better understand over time and also understand how to tackle them.
I think if I can sum it up, someone's challenges are someone's opportunities. So I think we are all in this for a better future and a better world.
Thank you very much.